Hey guys, hard to believe, but it's finally the last new lesson of the year, which is crazy to me. So we are going to finish up with talking about polar area. So pretty much I will tell you that a large portion of this lesson, I have it that, I was doing things by hand. If you look at the full answer key, so you can see the way the full integral was worked out with the trig substitutions and stuff. I'm not going to spend that whole time with the video going through that whole explanation because I post the whole answer key for you so you can look through that. I'm probably going to, most of these cases, just jump right to the final answer. And to be honest with you, for what we're going to be doing with polar area right now, actually you're not even going to be doing anything beyond today with polar area. You can really just use your calculator and that will get you to the answer. Okay, so let's begin with talking about the area of a sector. So what is that? That was back in geometry when you had a circle. And let's say you wanted to find a portion of the area of that circle. That's what we referred to as the area of a sector. So how did you figure that out? Well, if you think of the area of the circle as pi r squared, obviously that's the whole circle, but we want a fraction of the circle. So we want a fraction out of 360 if you think of it in terms of degrees. So for example, maybe this was something like, 60 over 360 or something like that, and that tells you that's 1/6 of that entire area. Or if you do it in terms of radians, which is where the formula for today is going to come from, or the basis of our formula for today, what you can think of is out of 2 pi, your theta out of 2 pi multiplied by pi r squared, and that's actually the same relationship that you just see in that one to the left, except for the fact that now it's in terms of radians. If I clean this up, my pi's will cancel, and I'm left with 1/2 times theta times r squared, okay? So that's the formula for the area of a sector. So area of a sector is 1/2 theta times r squared. Okay, so the other thing that's going to be different when you think about area in terms of polar is that it's not really area bounded between a curve and the x-axis or curve and the y-axis. It's more, what is the area when I go from this first angle, if you will, of rotation kind of, to this last angle. And what happens is that you actually end up having like an infinite number of little sectors inside here. So that's why we're basically going to end up integrating something like the area of this sector formula, but obviously there's going to be a couple changes based on the fact that you're now doing stuff with calculus. Okay, so if you go down to the area formula that we have here below, again, you can see some similarities with the formula for the area of the sector that I just had mentioned before, except obviously now again modified for calc. As you take the integral from a to b, so alpha to beta, that's what you can see when you look at these two right here. That's basically like your starting angle of rotation to your final angle of rotation. Instead of it just being a strict theta by itself, theta changes as you work your way through this entire region. So that's why it's d theta. And then I still have that 1/2 and that r squared. So again, there's a lot of similarities with stuff that you've done before, except for the fact that obviously now, again, slightly different formula. Okay. So let me just erase that. So let's go ahead and take a look at example number 1. I would encourage you to take your graphing calculator or pull out Desmos and actually, graph what this function actually looks like. What you're going to need, because this one says find the area bounded by the graph of r equals 2 plus 2 sine theta. This graph, if you actually put this on a grid, and I apologize because this is not a great sketch, it actually, comes back and connects back with itself, so that's why it's bounded just within the graph itself. There's no specific interval already given to you. If there was, that would make the integral really easy. Okay, so I would encourage you to take your graphing calculator, graph what this function looks like. Basically, you want to find out what is the interval that you can graph this function so that doesn't trace back over itself. Where does it begin? And you'll notice that if you graph it on the window from 0 to 2 pi, it will graph your entire picture here without tracing back over itself. If it starts tracing back over itself, you're adding additional area that you don't need. So if I use the formula that I have above, 1/2, okay, on the interval from 0 to 2 pi, it makes a full curve. It doesn't trace back over itself, and it completes this whole cycle all the way around this graph. My r is that 2 plus 2 sine theta squared d theta. Again, there is like a lot of trig substitution stuff that goes into this if you want to do it by hand, and I worked that whole thing out, including using double angle formulas and things like that in the answer key if you'd like to go back and see the whole thing worked out. Eventually, you'll see that this comes out to be an exact value of 6 pi. Again, for today, I really don't mind if you use your graphing calculator, but I wanted to at least have those, the full solutions there so you can see a little bit about how the trig substitution works. Okay? So if you take a look at example number 2, this time you're finding the area of one petal of this function. Okay, so when you take a look at this graph, you're going to see it looks something like this as I graph that first petal. So if you notice, I'm starting at 0 and I'm coming back to 0. So I basically have to take the equation I have and set it equal to 0, see 2 places that it equals 0, and use that as my window for where my integral is going to happen. Okay, so if you take 2 sine of 3 theta equals 0, this would give you the sine of 3 theta equals 0, dividing both sides by 2. What I usually like to do is replace 3 theta with something like x or u or something like that. So if you think of it as just x for a second, where is sine of x equal to 0? Sine of x equals 0 at 0, pi, and 2 pi. Now, I'm really not going to need that last point there, that 2 pi. I just need the first 2 times that it equals 0 so that it makes that first petal. So I'm just going to ignore that last one. Go back and replace x with 3 theta. So I have 3 theta equals 0, 3 theta equals pi, and eventually I'll find out that this gives me theta equals 0 and theta equals pi over 3. Okay, so there are the bounds on my integral. So as I set up my integral, it's 1/2 r squared d theta. So my r is 2 sine of 3 theta squared d theta. And it will be integrated on the interval from 0 to pi over 3. And again, if you're not sure about, like, does that actually make one petal, go on your graphing calculator and graph what this function looks like on this window. Or like I said, if you don't have a graphing calculator, Desmos would do a great job. Again, to solve this, it requires using some trig substitution, specifically with double angle formulas. Again, I've taken a lot of care to write those full solutions out for you in the answer key posted on Google Drive. So I encourage you to look there if you want to see the whole thing worked out. Again, for today, I'm really okay if you just want to use your graphing calculator. Okay? So, as I start getting into some of these more involved questions, okay, so specifically when you're finding the area bounded between two curves, a lot of it is going to have to do with thinking about angles of rotation. Remember that sometimes angles can be expressed in different ways, but they really mean the same location. It is in a way going to be kind of like upper minus lower like we had done before, but obviously again different cross-section formula, so you're not doing like pi r squared, you're doing again based off area equals integral of 1/2 r squared d theta, except now when you have two functions it's going to be something involving the outer function and something involving the inner function. So it says determine the area that lies inside of r equals 3 plus 2 sine theta and outside r equals 2. Okay, so what we're looking at in this particular situation, okay, you'll notice that there's an intersection at this point, and there's an intersection at this point. So the question is, am I finding the area as I rotate from this one angle of rotation to the other? Obviously, you can see the area is not shaded in that section. It's more like, okay, am I now going from the other one? So I have to, because remember, you're always rotating around to the left. So this is the situation you're dealing with. So I have to think about, how do I describe this angle so that it's my starting place, and this angle so that it's my finishing place? And then I think it's pretty clear at this point. You can see which function is on the outside, which function is on the inside, and plug it into your formula. But we're going to need to do a little bit of solving trig functions to be able to figure out what are these actual intersections. So if I set these two functions equal to each other, 3 plus 2 sine theta equals 2. You'd minus 3 from both sides and get 2 sine theta equals -1, or sine of theta equals -1/2. Okay, if you go back to thinking of special right triangles and all your exact value and trig stuff, you'll find out that this gives you two solutions. 7 pi over 6 is like 2/10, so this is like 7 pi over 6, and this is 11 pi over 6. So if I were to set up my integral to go from 7 pi over 6 to 11 pi over 6, here's where the problem would be. that's as if I'm rotating in that section that I don't want to be rotating in. I need to be making sure that my lower bound, that I'm starting at this location and rotating all the way around through to get to 7 pi over 6. So if you think back to what you know about trig functions, specifically like coterminal angles, you should probably know that 11 pi over 6 can also be represented in a different way. Specifically in this case, we're going to use the negative version of the angle of rotation. So 11 pi over 6 can also be represented as negative pi over 6, and that's how we set this up so that we're going from a lower bound to an upper bound as we rotate the correct direction about this grid. Okay, so as I set this up, 1/2 integral from negative pi over 6 to 7 pi over 6. And again, now it's going to be outer function, so that's that 3 plus 2 sine theta squared minus the inner function, which is 2 squared d theta. Okay, when you eventually work that out, here's what the exact value comes out to be, 11 radical 3 over 2 plus 14 pi over 3. Okay, again, you can leave it as a decimal answer, that's fine. I have all the trig substitutions worked out in the answer key if you would like to see them like that, but you really don't have to. Again, this would be something like, I think this would be something more like set up but do not solve, or you would have a graphing calculator if you were going to actually solve something like this on the AP exam. Okay, so you'll notice in the next example, I'm still dealing with the same two functions, except now I'm using a different portion of the angles of rotation. Okay, so if you remember previously, we had rotated from negative pi over 6 all the way around to 7 pi over 6, and that's how we were able to get the area of this region. Well, now we use a different set, angle of rotation that we work our way through. There becomes now a different outer function, a different inner function. If I look on the interval now, from 7 pi over 6 actually to 11 pi over 6. Instead of thinking of it as the negative angle anymore, now think of it as you're going from your smaller angle to your bigger angle. That's why we would end up seeing that in this case, we'd have an integral that goes from 7 pi over 6 to 11 pi over 6. You're still going to have that 1/2 in the front. And this time you'll notice that the outer function is actually the circle. So 2 squared is going to go on the outside, and then that 3 plus 2 sine theta squared d theta is going to go on the inside. You can see this will end up having, a similar kind of area value. This is the exact value. If you want to see the exact answer, go ahead and look at our Google Drive page. But again, decimal would be fine for just now. I think you should be able to do any of the homework questions using your graphing calculator without a problem. Okay, I'm really trying to focus a little more on the setup. Now, the one that I think is going to be a bit of a challenge would be something like number 6. So it says determine the area that is inside both r equals 3 plus 2 sine theta and r equals 2. So actually what you kind of need to do in this problem is think back to shaded area from when you were back in algebra. If you notice in this case, I basically am finding the area of the circle, right? So I'm going to have something with pi r squared as like the first part of what I'm finding my area from. So that would be pi times 2 squared. And then I have to subtract away from it that leftover part, okay? So if you notice, it's like this piece that has to get removed, if you will, from the circle. Well, if you think about what we just did here, look back to the previous question, this is the exact area that I'm trying to subtract. So if I take that, 4 pi, if you will, and minus the 11 rad 3 over 2 minus 7 pi over 3, that would be actually how you get your answer. And you can leave it like that. If you want to simplify it, it becomes 19 pi over 3 minus 11 radical 3 over 2. Again, I don't think you need to simplify it, but that's the exact value. So I would tell you that if that was if that was a question that you ended up getting, you'd have to know, okay, I'm going to have to go through and do this whole calculation as one part of this, and then make sure that that's getting subtracted from the other calculation, all as this one problem, if it wasn't like a part B or a part C of a previous question. Okay? So again, the main idea is really think about what are the angles of rotation that you're working your way through, whether it's you're working your way, through a diagram to get from one intersection with the origin to another, or maybe it's something where you're rotating, where you're looking at one function in comparison to another. Again, always make sure your bounds are going from a lower angle to a higher angle, so think about those coterminal angles. And again, fundamentally, the formula is based on the area of a sector, 1/2 r squared d theta. Okay, congratulations, guys. You made it.